Hello, in this video I will give a brief description of our research on unsupervised blind image deblurring based on self-enhancement. In real-world blind deblurring tasks, the degradation is much more complex than in synthetic datasets, and obtaining paired data in real-world scenarios presents significant challenges. The above factors lead to a high demand for the methods that do not require real paired samples. Unfortunately, due to the high difficulty and challenges of unsupervised deblurring methods in training, there is still very little relevant research in this field. In this work, to ensure the generated blurry images are closer to the real blurry images, we propose a novel redegradation principal component consistency loss, which enforces the principal components of the generated low-quality images to be similar to those of redegraded images from the original sharp ones. Furthermore, we introduce the self-enhancement strategy that significantly improves deblurring performance without increasing the computational complexity of network during inference. Through extensive experiments on multiple real-world blurry datasets, we demonstrate the superiority of our approach over other state-of-the-art unsupervised methods. This is the overall network framework. In Generator, we effectively utilize unpaired sharp and blurry images to synthesize pseudo-paired datasets. Inspired by Cyclogen, we design a GAN structure that transitions from original sharp to synthetic blur to reconstructed sharp to secondary synthetic blur, as shown by the red and blue arrows in figure. The Degradation Guide Information Generation module, providing ample pseudo-paired data for deblurring. Considering that the unsupervised deblurring framework's performance mainly relies on the blur image generator's capability, and also considering the challenges in GAN training, we further introduce extra to process to enhance the qualities of the synthetic images. We optimize the following loss function to train the reconstructor. In order to implement the self-enhancement strategy, keep the reconstructor trained in the last round fixed to guide the generator to learn degradation information more accurately, generating more realistic pseudo-blurry images. Subsequently, retrain generator, discriminator, and reconstructor until reconstructor reaches convergence. Finally, repeat the above process, progressively replacing and enhancing the reconstructor until obtain the best performing reconstructor. Therefore, we can obtain the complete loss function and adversarial loss. The basic idea of the SE strategy is to use the results of the previous phase as feedback information to guide and improve the training of subsequent stages. A comparative analysis with existing typical geometric augmentation methods, as presented in figure, reveals that the SE strategy markedly boosts performance with slightly additional training cost, without imposing extra complexity or testing overhead. It demonstrates the effectiveness of SE strategy in image deblurring. Although adversarial losses can effectively improve the performance of the generator and discriminator, leading to more accurately synthesized realistic blurred images, the data synthesis process is highly susceptible to interference from the inherent information in blurred images, such as content and color. By introducing blur kernel prediction in principal component constraint, the loss ensures the principal components of the synthesized low-quality images align with those of redegraded images from the original sharp ones, which can decrease the impact of noise interfere in the blurring process. We use the kernel estimation network to estimate the blur kernel of the blurry image, and then utilize this kernel to further reblur the sharp image. Subsequently, we maintain the principal component consistency between sharp image and the synthesized blurred image by introducing the L1 norm loss. Finally, we obtain the total loss function. This table presents the PS, NR, and SSIM results for various single-image deblurring test methods on the GoPro, HIDE, and RealBlur test datasets. It is evident that our proposed method outperforms other unsupervised methods. It's worth noting that all the mentioned models are trained on the GoPro dataset, which further demonstrates the excellent generalization performance of our method from GoPro to other real-world datasets. We compare the visual deblurring results of different unsupervised methods on the GoPro, HIDE, and RealBlur datasets, as presented in figure.